Have you ever actually stopped to think about this? If the electrons inside a wire are literally inching along slower than a snail, how on earth does your ceiling light turn on the exact milliseconds you flip the switch? It's kind of a crazy paradox, right? But answering it actually unlocks the secrets of basically our entire modern world.
So let's just dive right in. Welcome to this explainer on current electricity. Today, we're going to take this incredible journey together. We'll start way down in the microscopic, chaotic world of atoms and electrons, and we'll zoom all the way out to the macroscopic rules that govern massive power grids. Here's our roadmap for today. First, the basics of electric current. Second, drift velocity and electrons. Third, Ohm's law and resistance. Fourth, cells, EMF, and internal resistance. And fifth, solving complex circuits. All right, let's kick things off with Section 1, the basics of electric current.
So at its core, electric current is simply the rate at which electric charge flows through a cross-section of a conductor over time. The formula for this is I equals Q divided by T. Now, current is a scalar quantity, meaning its direction doesn't change how it adds up. But the really crucial takeaway here is that when we say a wire has a current of 1 ampere, that just means exactly 1 coulomb of charge is passing a specific point in that wire every single second.
Now, we've got to talk about a massive historical mix-up. Back in the day, early scientists hypothesized that positive charges were the things moving through wires, flowing from the positive terminal over to the negative terminal. And they set this up as conventional current. Well, it turns out they guessed wrong. Factually, it's the negatively charged electrons that are doing the flowing, and they move from negative to positive. But honestly, just out of pure habit, we still use that old conventional current direction on our circuit diagrams today. Kind of funny, right?
And that brings us to the two main flavors of current electricity. First up, we have direct current, or DC. This flows in one steady, constant direction. Think of the battery that's probably running your laptop or smartphone right now. On the flip side, we have alternating current, or AC, which periodically reverses its direction. AC is the stuff flowing out of your wall sockets, delivered by massive power grids, mostly just because it's so much easier to transmit over really long distances.
Moving on to Section 2, drift velocity and electrons. Okay. To really picture what's happening inside a conductor, I want you to imagine free electrons as people trying to run through a super crowded, chaotic hallway. They've got high thermal energy, so they're darting around at absolutely incredible speeds, but they're constantly violently colliding with the positive ions of the metal. Because of all this chaotic, random bouncing around, their average velocity is essentially zero. I mean, they aren't actually getting anywhere, at least not until we apply a voltage. The moment we connect a battery, an electric field is established almost instantly. This field pulls all the electrons collectively. But remember, they're still bumping into all those ions, so they only manage this tiny, really slow average forward movement that we call drift velocity. And when I say tiny, I mean tiny. It's roughly 10 to the power of -4 meters per second. Like we said earlier, literally slower than a snail. But because that electric field pushes all the billions of electrons in the wire at the exact same time, the effect, like your light bulb turning on, happens instantly. Now, right between all those microscopic crashes, an electron gets a tiny, tiny fraction of a second to just accelerate freely under the electric field. We call this peaceful little window the relaxation time. And what's really fascinating here is that if you heat up the wire, the atoms vibrate much more aggressively. This means the electrons collide much faster, and that brief relaxation time drops significantly. Which perfectly sets up Section 3, Ohm's law and resistance. This brings us to what is probably the most famous rule in basic electronics, Ohm's law. It states that the voltage across a conductor is directly proportional to the current flowing through it. That gives us the classic formula, V equals I times R. So, simply put, if you double the voltage push, you double the current flow. But there's a massive caveat here that almost everyone forgets. This only works if the physical conditions, especially the temperature, remain perfectly constant. Because temperature messes with those electron collisions, resistance isn't always static. For normal metals, if you crank up the heat, collisions happen faster and resistance increases rapidly, often exponentially. For alloys like manganese, the resistance increases, but much, much more slowly, which actually makes them great for standard resistors. But then you have semiconductors. These are the rule breakers. If you heat up a semiconductor, it actually frees up more electrons to conduct, so its resistance actively drops. This weird, counterintuitive behavior is literally what makes modern computing possible.
And that leads us to a super vital truth. Ohm's law is not magic, and it's definitely not universal. Elements that don't obey it are called non-ohmic. For instance, vacuum diodes totally break the rule. Semiconductors like gallium arsenide have these incredibly complex voltage-current relationships that look absolutely nothing like a straight line on a graph. So always remember, Ohm's law is a fantastic, useful model for standard metals, but it's not some universal law of nature. All right, let's jump to Section 4, cells, EMF, and internal resistance. You know, we tend to think of batteries as these perfect, endless sources of voltage, but they really aren't. A battery creates power through chemical reactions inside an electrolyte, but the ions inside that electrolyte, they also crash into each other. This creates a natural, totally unavoidable traffic jam inside the battery itself, which we call internal resistance. You'll usually see it represented by a little lowercase r in circuit diagrams.
Let's actually anchor this in a real-world calculation. Imagine a standard 12-volt car battery. Because of the chemicals inside, it has an internal resistance of about 0.4 ohms. If we use our equations, the maximum current you can physically draw from this battery without just melting the thing is exactly 30 amps. Now, because real cars require a massive surge of current to start the motor, we're talking hundreds of amps here, this particular battery wouldn't even be strong enough to turn over an engine.
So this internal resistance creates a real difference between what's printed on a battery's label and what you actually get out of it. The electromotive force, or EMF, is the maximum theoretical voltage when absolutely no current is flowing. It's your open circuit voltage. But the very second you connect it to a circuit and start drawing current, that internal resistance eats up a tiny bit of the power. What you actually get out is called the terminal voltage, and it's always going to be slightly lower than the EMF while the battery's discharging. Okay, moving to our final topic, Section 5, solving complex circuits. When you're dealing with multiple intersecting wires, multiple batteries, and loops tucked inside of other loops, simple Ohm's law just completely falls apart. Enter Kirchhoff's laws. These are basically the ultimate cheat codes for solving complex circuit puzzles. They rely on two fundamental truths of the universe. First, the conservation of charge, meaning whatever current enters a junction has to leave it. And second, the conservation of energy, meaning the total change in voltage around any closed loop must always equal exactly 0.
Now, the thing that usually trips people up with Kirchhoff's voltage law is the sign convention, figuring out when to use a plus or a minus. Luckily, there are 3 foolproof steps to nail this every time. First, just pick a direction to travel around the loop. Second, if your path goes in the same direction as the current through a resistor, you're losing energy, so write down a negative I times R. Third, if you cross a battery from the small negative terminal to the large positive terminal, that's a step up in energy, so you add the EMF as a positive value. Honestly, just stick to these rules, and the math will solve the puzzle for you every single time.
One of the most famous applications of Kirchhoff's rules is something called the Wheatstone bridge. It's this incredibly clever circuit used to find an unknown resistance with massive precision. It uses 4 resistors arranged in a diamond or quadrilateral shape, with a meter sitting right in the middle. By tweaking the known resistors until absolutely 0 current flows through that middle path, we reach a state of perfect balance. And when it's balanced, this beautiful golden ratio applies. The ratio of the top resistors perfectly equals the ratio of the bottom resistors. So P over Q equals R over S. It's essentially an elegant mathematical solution that's been built physically right into the hardware.
And wow, that brings us to the end of our journey. We've seen how mastering the chaotic, snail-pace drift of microscopic electrons allows us to manipulate resistance, harness chemical EMF, and solve incredibly complex webs to do things like light up entire cities. But looking forward, if semiconductors completely changed our world by breaking Ohm's law, it leaves us with a thrilling question. What bizarre new materials, superconductors, or battery chemistries are being discovered right now that will completely revolutionize how we store and transmit energy tomorrow? Thank you so much for joining me on this explainer, and definitely keep questioning the science around you.